Good morning, it's Jeremy. It's Tuesday, December the 5th. And in the previous two videos, I looked at LoRa, which is a communications protocol for low power battery operated devices. And in the first video and blog, I looked at creating the symbols, the spread spectrum chirp symbols that LoRa uses. And in the second video, I put two 950 megahertz transceivers back to back and sent a packet. So I'm just getting into LoRa and experimenting with it. So I thought I'd do another simulation video to show you how robust LoRa is. And here's a picture from the blog post. What I've got here is the various, I've got a spreading factor of 3. The spreading factor is generally from 7 to 12, but just for illustration purposes, I've got a spreading factor of 3, which means 8 symbols. So there's the first symbol, there's the second, there's the third, etc., all the way up to the 8th. In Scicos, the index starts at 1, not 0. So instead of 0 to 7 symbols, I've got 1 to 8. So those are the various possible symbols. And what happens when you transmit a symbol? It gets corrupted by noise. So what I've done is I've read into a correlator, which we'll see in a minute. I've read in all the possible symbols there from 1 to 8. And then what I've done is I've received a symbol 1 and I've corrupted it with a lot of noise. And then I do the correlation, the match between each one of these, and you'll see that even with noise, symbol 1 correlated against itself gives you this peak here, which is a lot stronger than any other peak. So let's say if we were to say that symbol 1 correlated with symbol 7 was the actual received symbol, you see that that correlation peak is lower. So there's a table of the specs, which we've had in the previous two videos. So those are from the LoRa Alliance, reference 1. And this is the code I used to create the symbols. So I've got two structures. The first structure reads in symbols 1 all the way up to 8. And structure 2 reads in symbol 1 8 times. So here's the correlator. Basically what happens is you have the this is what the receiver would be doing. It would be comparing what the received symbol was against a library. And of course, there's other techniques to make this a lot simpler, but just for illustration purposes. So I've created 8 symbols, which I'm reading in here, and then I've got symbol 1, which I'm adding noise to, and then I'm multiplying them together, which is basically taking the inner product of their sample values. And then I'm integrating that product to see how well they match. And you can see here from the integration that symbol 1 against symbol 1 gives you a nice peak here. I think it goes up to something like 2.7. And the closest other peak is down here. Let's say symbol 1 was compared against symbol 7. That would give you like 1 point something. So there's a great difference between that and that. So the receiver would decide that symbol 1 was sent. This is when I've set the noise generator at 0. Here I'm adding a bit of noise. We'll see in a minute how we do that. That's a noise generator set to 0.1. And again, you can see that symbol 1 compared with itself is a much greater than anything else. And then finally, what I do is I add a lot of noise. And this is a threshold. So here the signal generator is set to 1. The signal-to-noise ratio, I'm just taking a visual signal-to-noise ratio. It's not very accurate, but just to give me an idea, it's around minus 7 dB. At around minus 7 dB, what happens is that you can't say that symbol 1 was sent. You're going to make a mistake for sure. So that's the threshold. So we can say that around minus 7 dB, you're going to start to take a lot of errors. Okay, so that's what I've summarized in this table here. There's noise at 0.0 all the way up to 1.0. So we're saying around minus 7 dB, you can't use it. So if you back that up a little bit, let's say the signal to noise ratio was around, let's say minus 3, minus 4, something like that, then you could probably use it with, a bit error rate, maybe of 10 to the minus 3 or 10 to the minus 2 or something like that. This is not a strict BER versus signal to noise ratio test. This is just for illustration purposes. So let's actually go to the model itself. So there's the code there, and down here I create the structure. So the first structure is all the various symbols. The second structure is I'm just reading in symbol 1 8 times because I'm going to compare it against all of these. And then there's the model. So those are my 8 symbols coming in. Actually, they'd be stored in the receiver in some way. And then symbol 1 comes in and you're adding the noise here. So in the context, what we do is we set up a variable n and you adjust the noise by giving it a different value here for n. And if you look at this, it's just a random number generator used as a noise source. So what I'm doing is I'm changing the sigma here. I'm just upping n to create more noise. So you take the receive symbol and you correlate it with all the possible values of the symbols. There are 8 of them. You correlate it by multiplying them together, and then you integrate, reset after every symbol, and then I'm using just a factor of 10 to multiply this up so we can see the output of the integrator. Let's do an example here. Where we go, run. So that's down here, it's symbol 1 plus noise. This is symbol 1, symbol 2, symbol 3, all the way up to symbol 8, and that's the correlation. So we don't have a lot of noise, and you can see the correlation here. Symbol 1 in itself is very strong. So the beauty of LoRa, when you have a larger spreading factor, is that you can operate as a spread spectrum system, and you can get good performance even if the signal to noise ratio is less than 0, which means that the noise is stronger than the signal, which is pretty amazing.